All right, let's dive into one of the biggest questions in all of science. How do we learn? I mean, it's something we do literally every single day, but the process itself, still one of the most profound mysteries out there.
Think about it. How are you learning right now, just by watching this? How does your mind take in all this new information, start to make sense of it, and then, hopefully, store it away for later? This simple question actually hides a really deep and fascinating debate about how our minds are even built.
Think about it like this. What's the real difference between learning to ride a bike and learning the rules of a new board game? One is all about feel and balance and instinct, right? It's physical. The other is pure logic, symbols and abstract instructions. Well, this very contrast between intuitive skills and logical rules is right at the heart of a huge scientific debate.
And that debate really boils down to two competing philosophies for how the mind works. So, is your mind like a master architect designing the perfect blueprint for a solution, or is it more like a physical brain slowly rewiring itself through trial and error?
So on one side, we've got what's called the rationalist view. This idea says the mind acts like a perfect statistician. It weighs all the evidence and designs the absolute best, most optimal solution to a problem. But on the other side, you've got the mechanistic view. This sees the mind as a network of simple neuron-like parts that learn by physically adjusting the connections between them. One is about finding the perfect plan, the other is about building the machine that gets the job done.
That rationalist approach is often modeled using a really powerful idea called Bayesian inference. Now, the core concept here is actually pretty intuitive. It's just that your mind is constantly updating its beliefs. It takes what it already thinks is true, its prior beliefs, and it combines that with new data to make the best possible guess. This approach is amazing for explaining what our mind is trying to do and why it's such a good strategy.
The mechanistic approach, on the other hand, is called connectionism, and you can just picture it as a huge network of virtual neurons. Here, learning isn't about finding some perfect abstract solution. Nope. It's about gradually strengthening or weakening the connections in this network through trial and error. What's so cool about this is it gives us a potential how, a physical process for learning that's actually inspired by the brain itself.
Okay, so we have these two huge ideas, but they both run into this really fascinating puzzle when it comes to something called generalization. How we apply what we've learned to things we've never ever seen before. Let's dig into that.
So for just recognizing patterns, there's this absolutely beautiful theory from a researcher named Roger Shepard. He discovered that we seem to have this psychological space in our minds. The closer two things are in this mental space, like two really similar shades of blue, the more likely we are to generalize from one to the other. It's just this elegant, powerful way to explain how we learn from what we perceive.
But here's the twist. What about learning a totally abstract rule? Like, think about grammar. The rule for making a verb past tense is usually to add ed. Now, you can apply that rule to a brand new, made-up verb you've never heard before. Say, to pling. You instantly know the past tense is plinged. How on earth does that work?
This is exactly where those mechanistic, connectionist models kind of hit a wall. As researcher Gary Marcus pointed out, these networks are fantastic at recognizing patterns in the stuff they've been trained on. But they really struggle to apply a universal, abstract rule to a completely new example that's way outside their experience.
So, here's the crucial point. It seems like our minds need to do two very different jobs. One is recognizing those fuzzy, similarity-based patterns, like Shepard's colors, and the other is applying sharp, absolute rules, like grammar. A single theory has a really hard time explaining both of those things. It strongly suggests our mind isn't just one kind of machine.
So where does that leave us? Well, modern science is now suggesting that the answer isn't about picking a winner in this debate. Instead, it's about figuring out how the brain cleverly combines both of these powerful strategies into one elegant system.
The answer is a partnership. That's right. Our brain doesn't choose between being a blueprint designer or a physical machine. It actually has systems that do both. It's like a mind of two minds, and they're working together.
Researchers like Daw, Niv, and Dion came up with this brilliant dual system model. First, there's the goal-directed system. We can call this the planner. It's slow, it's careful, and it really thinks through the consequences of its actions, like when you're figuring out a new route in a city. And then there's the habitual system. Let's call that the autopilot. This one is fast, automatic, and just runs on instinct and repetition, like your daily commute to work when you don't even have to think about it.
So how does the brain decide which one to use, the planner or the autopilot?
Well, it all comes down to a smart trade-off based on uncertainty. When a situation is new or complicated, the brain leans on the flexible planner. But once a skill is totally practiced and the outcome is predictable, the brain saves a ton of energy by handing the controls over to the efficient autopilot. It's this dynamic process where the brain just gives control to whichever system it trusts more in that specific moment.
So, we've gone on this journey from these huge competing philosophies all the way to this beautiful synthesis of how the mind's software might actually work. But this brings us to the ultimate mystery, the final frontier. Even with these powerful theories, the biggest question of all still remains. How does the physical hardware of our brain, those billions of neurons and trillions of connections, actually run these incredibly complex programs? That is the question scientists are racing to answer today.